Now that we've largely handled substitution versus elimination, or at least we've done both kinds of substitution reactions and both kinds of elimination reactions, you arrive at the really challenging part of trying to tease apart which of the following reactions is taking place given a substrate that could go a number of different ways. And so this is truly a difficult place to try to figure out what's going to happen. And my advice here is to generate your own good flow chart to handle the situation, or perhaps generate your own chart. You can either take more of the Pelkey approach or take more of the Miller approach. Tables of stuff for the Miller approach, big flow chart for Prof. Pelkey. I personally don't think that there's much value in memorizing the information I'm about to give you, but I think in my talking through how I store this information away, you can find it helpful and find a way of categorizing this in a way that'll be useful. And for me personally, the best way to start thinking about it is actually a series of questions. So when I'm start to thinking about, will we do a substitution reaction or will we do an elimination reaction, what I'm really starting to do is think about, do I have a nucleophile at all? With no nucleophile, there's not going to be a substitution reaction of any type. We might still do an elimination reaction depending on what exactly is going on, but we can't do a substitution if we don't have a nucleophile. Likewise, do we have a base or not? Certain types of elimination definitely depend on a base. If you're doing an E2, you need a base of some kind, whereas E1 eliminations can be run in acid. So the presence or absence of base will bias you in one direction or another. Do you have a leaving group at all? With no leaving group, you can't do any of this chemistry. However, if you don't have a leaving group yet, do you have a group that can be converted into a leaving group? In which case, maybe you might be able to do some of this chemistry. You're getting the point. There's a lot of nuance here, and there's a lot of different questions that you could ask, which again is why it's not particularly useful to memorize any one person's take on this. Instead, what you want is the ability to take a blank sheet of paper and generate some kind of useful flowchart or chart. If you can do that, then you truly understand the issues at play. And if you can't do that, then my advice would be to practice. Generate a flowchart a couple of different ways. But when push comes to shove, you don't need to have this categorized in your mind so well as being able to solve problems. And so if you have a sheet of practice problems, you can work through those. Having said that, there is still some value in generating a chart like this in order to figure out what are the various things you need to be thinking about. So what do I have here? Degree of substitution. And fundamentally, the reason why I'm bringing up degree of substitution here at the end is not because it's not important. In fact, in many ways, it's the most important way. But it leads to a different chart. And so I have yes or no questions here, basically, and now I have choices. And here's where the flow chart really exists. And so I'll just simply point out that by degree of substitution, what I mean is primary, secondary, or tertiary. But there's resonance that's sort of lurking in the background as well. So if you have a primary with resonance, you need to think of it more like a secondary in terms of its ability to perform SN1 type chemistry or E1 chemistry. So flowcharts become tricky because you need to have these weird little offshooty questions, but I still think they're the right way to organize things. So with degree of substitution, the first question is, what is the degree of substitution of the thing that's going to serve as a leaving group? So again, the first question really might be, do you have a leaving group at all? Because if you don't, then none of this matters. If you have something that could be converted into a leaving group, then all of a sudden this chart comes into play. So if we have a primary of some variety, then you cannot perform an SN1 reaction, or you also cannot perform an E1 reaction. Caveat, if there's resonance involved, then primary plus resonance, different story. That's more like a secondary. But if you just have a plain primary, then you can't run carbocation style reactions with primary substrates. You can, however, run SN2 reactions and E2 reactions as long as you have a primary and a decent leaving group. Notice, of course, that I'm using red X's for this doesn't go and green check marks for yeah, you need to think about it. So with a secondary system, unfortunately, that's where things are complicated because everything is on the table. Substitution reactions are definitely possible. Elimination reactions are definitely possible. You're more likely to do eliminations if you have a lot of sterics beyond the secondary. Whether you have an SN1 or an SN2 will depend on what kind of solvent you have. Basically, this is the complicated one. Things are much more straightforward if you don't have a secondary, but if you have a secondary, then everything's on the table and all of your questions come into play. With the tertiary system, now an SN1 type reaction becomes very possible and an SN2 reaction is no longer possible. But the main reason why the SN2 reaction is no longer possible is because with a tertiary system, all of a sudden an E2 elimination speeds way up. The chances of being able to do an E2 elimination with any kind of base present are much, much higher if you have a tertiary. So the main reason why you can't do an SN2 is not because you couldn't do it in some sense, but because this becomes suddenly much faster. And so everything's biased toward E2. Can you do an E1? Yes, of course, but as long as you don't have one of the other reactions happening first. Solvent. If you have the right sort of solvent, then this will definitely work. So as long as you have an A product solvent, you can do SN2 type chemistry, and that will generally work. But if you have a mismatched solvent, say a protic one but an SN2 like nucleophile, then E2 eliminations become a bigger possibility. So keep in mind that if you have a nicely set up solvent that's aprotic, you're going to tend toward SN2. If you have aprotic, it could be E2, but if you have a mismatched one, that almost certainly biases you in the direction of elimination instead. In order to do the cation reactions, then you really need to have the right sort of solvent, one that can stabilize the forming plus and minus charges from your leaving group and the cation that will result. So if you have a protic solvent, of course, you're thinking that cations can form and SN1 and E1 become much more favorable. With a SN2 type reaction, you really need to have a nice matched solvent, an aprotic solvent that will increase the ability of the nucleophile to attack, which means an aprotic solvent. Whereas if you have something that's tending to dampen the availability of the nucleophile, what you're doing is increasing the chances that other chemistry gets involved. And so a mismatched solvent is more likely to lead to an elimination type reaction. Base nucleophile. Well, if you want an SN2 reaction to go, you need a good nucleophile, but it had better be not a base, because if you have a base, it'll be doing E2 elimination instead. So you want a good nucleophile, but not a base in order for an SN2 reaction to take place. Whereas over here, if you have a strong base, you're definitely going to be doing an elimination. And even if you don't have a strong base, it's still going to be biased toward elimination if you have a base at all. Meanwhile, SN1 type reaction, you need no base, you need a nucleophile, but it doesn't need to be a good one necessarily, it just needs to be okay. So you need to have a nucleophile, but it doesn't need to be a good one, because you're forming a carbocation and the carbocation is not going to be particularly discriminating. And an E1 is kind of the reaction of last resort. What I mean by that is it will happen as long as nothing else turns out to be faster. So if you've got a base at all, an E2 is going to be faster than an E1, and E1 is less likely to happen. If you have a good nucleophile, you're more likely to be doing an SN2 or an SN1. So E1 is what happens kind of if nothing else is happening faster. And so in other words, if you have a really weak nucleophile, if you don't really have a base, that's when an E1 can happen. So think some acid present and stuff like that. So these are the various things you need to be thinking about as you're encountering the potential substitution / elimination type reactions. And memorizing this chart will offer you very little value. Being able to generate a chart like this of your own, that offers substantial value.